Chapter 12, Deflection of Beams and Shafts. Let's attempt a very interesting problem in beams deflection. So we do have this configuration, and for loading shown and knowing the beams A, B, and D having the same EI, flexural rigidity, which is E modulus of elasticity times of inertia, we want to determine the reactions at all supports. So we want to know what RA, RA, RE, RD, and reaction at B is. Let's solve the problem. So first, let's go with the so as you can see in the figure, two simple support beam AB and D are located at the top of each other. So beam D is on the top of beam AB and intersect each other at center point C, and and C is exactly where the external concentrated force of P applied at center C. So let's start with the lower beam AB. So if we just consider there is a reaction force at center for beam AB, which pulls the beams down, we do know deflection at C, in this case we call it YC1, is RC reaction at C times the length of 2A cubed over 48 EI deflection of a simple support beam with delta for such beam is 48 R L cubed over 48 EI. Our reaction is RC, our length is 2A cubed over 48 EI. Likewise for beam at the top, so this is top beam DE. This is AB. If beams at DE go down by the amount of force which is applied there, beam AB prevent the maximum deflection. So there is a deflection due to force P, external concentrated load at the top, and RC from AB is just a pulling of force for due to resistance of AB. So in that case, YC2 is the combination of those two fighting force P minus RC times 2B this time, which is the length cubed over 48 EI. So we just replace the force. Resultant force is P minus RC for the top beam as we discussed. And due to consistency of deformations, so YC1 should equal to YC2. And if you make that equation, both deflection at center point resulted from each of those beams should be equal to each other due to consistency. C has no way to move down at the same amount of the delta. So if you equalize these two equations, it just gives you an equation based off RC. And if you solve that equation, it just gives you RC is equal to P times B cubed over A cubed plus B cubed, and at the same time A is equal to 4. A is equal to 4, which length of LAB is 2A, and LDE is Q is 5. If you replace the numeric value, it just gives you RC is equal to a 3.90, almost 97 kilopounds. For calculating the reaction at beam AB, just summation of moment about, for example, point A gives us 2A distance times RB minus RC times A 0. RB is gives the equation RB. Reaction at B is a half of RC, and that's 1.98 kilopounds. So due to symmetry, RA is equal to RB, and that's 1.984 kilopounds upward. The same for beam DE. Summation of moment above, for example, point D gives us a equation based off RE, P, and RC, and if you solve that, it just gives you RE is half of P minus RC. If you place, we already calculate, but RC is P is provided to be 6 kilopounds from problem statement. RD is equal to RE due to symmetry again, and it's 1.016 kilopounds, and again that's an upward forces. Yet the interesting part, so far we calculated all the reactions for this interesting problem, yet we can solve it in a way more interesting approach. If you remember in solution 2, if you remember in parallel situation, this is exactly where you can, this is the key to the solution. In beams AB, it says beam AB and beam CD, my bad, D are in parallel condition. So in parallel, delta is the same, but forces are distributed based on their stiffness of the spring or beams. So because the configuration of this scenario, it just says delta at center is the same. So that's a reminder of parallel condition. So in parallel scenario, delta remains the same, delta at C remains the same in both beams, and force is distributed based off their stiffness. So let's see what is the stiffness. So if you just consider beam AB, delta maximum is PL cubed over 48 EI, and L is equal to 2 times 4, which is 8 feet. KAB is stiffness of beam AB is 48 EI over L cubed. So this is stiffness. 48 over L cubed is the stiffness of beam AB. The same for beam DE. This time just consider the top beam DE. Delta maximum D is gain 40 PL cubed over 48 EI, and this time L is 10 feet. So KDE stiffness of beam D is 48 EI over 10 cube. So again, in parallel condition, force of each beams distributed based off their stiffness. So the stiffness of beam AB over the total stiffness times the total force, which is 6 kilopounds, and FD is stiffness of beam up beam over the total stiffness times the total force. Let's attempt force at AB, which is a 1. If simplify the factor out those parts, you can factor out, it's 1 over 8 cubed over 1, 8 cubed plus 1 over 10 cubed times 6 kilopounds. And if you do the math, it just gives you FAB is 0.60, almost 66 times a 6 kilopounds, which is a 3.97 kilopounds. Due to symmetry, RA reaction at A is to reaction at B, and is half of the force of beam AB. And that's exactly 1.98, which we already calculated from the previous method. And likewise, if DE is a stiffness of DE over the total stiffness, and this time 1 over 10 cubed is over 1 of total stiffness times the total force. And if you do the math, it just gives you this time FD is a 0.33 almost times 6 kilopounds. This is 2.32 kilopounds. And again, symmetry RE is equal to RD, and that's a half of 2.032, and it just says RD is equal to RE, and that's equal to 1.016 kilopounds. This is a very interesting example, and try to solve more problem in this category. Thank you.